Hello everyone, and welcome back to Bevy Basics, Game Development Essentials in Bevy. In episode 2, we're going to talk about resources, how to organize your code using features like bundles and plugins, and we're going to cover all the basics of 3D game development. So first we're going to talk about resources. Resources in Bevy are singletons, meaning there's only one instance of each resource available across all systems. For example, Bevy defines an ambient light. This resource can be tuned by setting the color and brightness when the ambient light is inserted to the scene, that is, we add it to the game world, models will be uniformly illuminated. We may also wish to define our own resources. For example, a game state resource with a isPlaying field, which could globally signal whether the game is active or paused, influencing systems like update position, such that when you pause the game, things stop moving. In order to do this, update position would take a game state resource as an argument. This is the same dependency injection with queries and commands that we learned about in the previous chapter. Update position can then check the isPlaying field to determine whether the spaceship should move. In this case, update position takes res game state. We're taking a read-only copy of the resource to be able to access its fields. We can also do the very same thing with res mute game state. This would allow us to mutate the fields. To define a resource, derive resource on any struct or enum. This is very similar to defining a component. You just define your data type and then you tell Bevy that it is a resource by deriving resource. Then, once you have your resource defined, you can insert it into the game world. There's two ways to do this. With init resource type, this can be used to add a resource to the world with its default values. Useful when you have straightforward default state and you just want to add it directly to the game world with that default state. Insert resource, on the other hand, requires you to provide an instance of the resource. This method is useful when you want to initialize a resource with specific values. We're going to move on to Bevy Code Organization, which helps you organize your applications. We're going to start by looking at bundles, and then we're going to move on to plugins. Bundles are a way to organize your components. The components of an entity usually are just a set of components passed as a tuple when you spawn the entity. This can be brittle, however, when you require a specific set of components on an entity for it to function properly. Bundles in Bevy are a collection of components that can be added to entities, ensuring consistency and reducing boilerplate. Bundles are usually used to define a common set of components that can be used across multiple entities. This way, the Rust compiler will return an error if you do not set all the fields of the bundle struct. Bevy provides numerous built-in bundles for common functionality, enhancing both ease of use and code clarity. Bundles can also be nested. For example, we might have a spaceship bundle that defines velocity and model. The model would then be a scene bundle that requires you to pass in all the attributes of that bundle. In the future, the spaceship bundle could be generalized as vehicle bundle. As your game expands and you have different types of vehicles, this would allow you to find all the shared components across all the vehicles in the game in this bundle. Alright everyone, now that we understand how we can organize our applications using bundles for components, let's talk about how we can architect our entire app using plugins. Plugins allow you to encapsulate functionality into separate, reusable modules. For instance, you could separate spaceship-related logic into a spaceship plugin and asteroid behavior into an asteroids plugin, each in their own file, and then add these plugins to your main Bevy app by importing them to the main file and calling add plugins. The only thing that a plugin needs to do in order to be able to be added to the app with add plugins is to implement the plugin trait. This trait defines a single method build. This method receives a mutable reference to the app, enabling you to add systems, resources, and other configuration. In other words, plugins are extremely flexible. You can configure and extend your Bevy application in any way you want. You just have a mutable reference to an app. After build is executed, your plugin has run and made the modifications to the Bevy app. Plugins can also nest plugins. You could call app.addPlugins inside of your own plugin. This allows you to really break down the hierarchy of your app and keep things modular. Let's move on from Bevy architecture and talk about some more fundamentals of 3D game development. Vectors are the starting point for dealing with 3D. A vector is just a thing with some direction and magnitude, and we're going to use that vector a lot in our application. We have lots of types of vectors. We have vec2s, vec3s, ivec2s, ivec3s, a lot of different vectors, but really they're just something that defines a value, just a floating point or integer value in multiple dimensions. So in 3D, we have a vector that's going to be used for the X, Y, Z axes. And vectors are great. They're flexible, they're easy to use, and we're just going to use them a lot. So, keep that in mind. We use vectors in combination with 3D coordinates to move game objects and define their positions in space. The y-axis in a 3D coordinate system in Bevy goes from bottom to top. So then you have the z that's going to be near to far. That basically means you drew a vector. It would come out of your screen pointing at you. You're going to have x that's going to go from left to right. All right, well, I hope you have at least a basic understanding of 3D coordinates and vectors, but we need to talk a little bit more about how Bevy represents these values. We have vectors that can store multi-dimensional data across 2D or 3D, but what about our game objects? How do we actually represent their position, their rotation, their scale? Well, luckily, Bevy provides a built-in component for us called transform, and this component holds information and is used to position our entities in our game. Let's cover each of these fields in the component. So the translation or position is basically a vector in 3D space that represents the position in the game world. The values of this vector are the coordinates of the entity along the X, Y, and Z axes. Translation is basically the equivalent of moving an entity. A lot of times you will mutate the translation of a transform in order to move something across the screen or teleport it across the world. Rotation then is just the representation of the orientation of the entity. It uses a quaternion to represent that value, a mathematical way to represent rotation. You don't need to worry about understanding it. There's many helper functions that allow you to do simple operations without really understanding the details. For example, rotating around a specific axis by a certain number of degrees. Final thing here, scale. This just defines the size of an entity. Very straightforward. It's a three-dimensional vector because you could scale it in any of the axes. So if you wanted to scale something to make it quote-unquote taller, you could increase the y-axis of the scale. So we have all those three things. You can use them to basically modify the properties of our objects. It's important to note that a lot of times you're just going to get transform automatically when you create an object in Bevy using certain bundles. For example, a spatial bundle, a scene bundle. These are bundles that you'll use when you're using 3D objects. Let's say you're loading something from a model. You're probably going to use a scene bundle. Let's say you're just creating some spatial entity that doesn't have any visuals, you might use a spatial bundle. Those bundles by default will include a transform. Next up, global transform and entity hierarchy relationships. So we know what a transform is, right? It defines how an object's position, rotated, scaled in the world. But what if we had a planet and the planet had trees and the trees had leaves? We might not want to define each leaf transform globally. It might be relative to the tree, and this might make it easier. Because what if we rotate the tree as a whole? That is, the tree starts falling over. We also want leaves to move with the tree. Even if those were represented by separate objects, they're still associated. In essence, you could think of the leaves as children of the tree. And this is where we get the concept of an entity hierarchy. We can basically have certain parent objects that have child objects. And when you spawn a hierarchy of entities, each child's transform is relative to its parent. Transform stores local position, rotation, and scale. And global transform stores the entity's global position or absolute value, rotation, and scale. Whenever you modify a transform, it's going to be synced by Bevy to the global transform. You cannot modify global transform yourself. Basically, it is an immutable component. It's going to be calculated internally by Bevy. So that really gives you a super quick breakdown. If you see global transform, you'll know what it is. We're not going to do too much with these entity hierarchies in this video. And one final note is that if you have the root object, that is, it's not a child of any other objects, that the transform and the global transform are going to be the same because the transform is going to be relative to 0, 0, 0. Okay, we have transforms, we have vectors, we have 3D space. Hopefully this is getting us towards a place where we can actually view our objects in the world, but unfortunately we're not there yet because we need one more critical piece, and that's cameras. Cameras determine which part of the game is visible to the player on the screen. So without a camera, even if you spawn something into the world from a file, there's going to be nothing to see because the game doesn't know what to render, right? And in order to do that, you're going to spawn a camera into the world. Luckily, there's built-in bundles to do that, and you're going to just use a camera bundle 2D or a camera bundle 3D, and this is going to help you position basically the perspective of what the game should show. You can just use commands.spawn. Cameras in Bevy are just entities, and you're going to specify a transform. And you can use helper functions like looking at, and what that's really going to do behind the scenes is modify the rotation of the camera. So in this case, if we spawn a camera with camera distance as the Y value, that means it's going to be above the scene. If we say looking at vec3 0, that's going to look at the origin point 0, 0, 0, and then we're going to say vec3 Z, and that's going to specify what the top of the camera should be pointing at. I'm going to show you a visualization of this really quickly, but as a starting point, we can just think of cameras as entities with a built-in camera bundle such that when you specify all the components, Bevy will know that you've added a camera to your game, and thus it will know how to render the game objects to your screen. Okay, so here's an example illustrating what a camera looks like in 3D space. Obviously, when we're actually playing the game, we're not going to be able to see the camera, right? Because the camera is behind the screen. But here's a view in Blender, which is popular 3D modeling software that can kind of show you basically the projection of the camera and what's going to be rendered on its screen. We can see a top-down visualization using the very same camera bundle and positioning that we saw before. So here the camera, let's say it's positioned at camera distance on the Y and then 0 on the X and 0 on the Z. That means it's above the 0, 0 position, and let's assume that right now the spaceship is at 0, 0, 0. So in this case, the spaceship will be in the very middle of the camera's view, and the camera will be pointing down, looking at the spaceship, and the top of our screen will be the top of the Z-axis. So this is not the traditional 3D orientation. This is like a top-down orientation, and that's how we can kind of see. With cameras, we can switch the orientation and we can really make it so the camera looks any direction we want. Sometimes this can be disorienting, but it's nice because it gives us the flexibility to see our worlds in any way we want. Let's look at a real quick video of what this might look like. So here we have a spaceship in the exact same position in Blender as before. We're just rotating around the viewport. The yellow box here is going to be what we see on the screen. What you've learned just in this video, that's the foundation of all 3D game development. So if you have these skills and you understand vectors and transforms and 3D coordinate systems, you can start building a 3D game. I personally came to Bevy with no background in 3D game development. I think Bevy actually makes it more accessible to us. So let's real quick recap the concepts that we've learned. Vectors represent and are used to manipulate positions, directions, and other spatial properties. 3D coordinate system comprises X, Y, and Z as axes. We use vectors in combination with 3D coordinates to move game objects and define their positions in space. Transforms are used to translate, rotate, and scale entities. Cameras define the player's viewpoint. Let's talk more practically about how you can get started building a 3D game. Let's say you want to build a prototype for a platformer. You're first going to need some models. And I highly recommend downloading some models from PolyPizza. It's a great way that you can get just free low poly assets and you can prototype your game. In this tutorial, we're going to be using some space assets that are found on PolyPizza, and I will link those in the descriptions for all of you. Once you have those models, then you're going to have to actually get them into your game engine, right? So you have a model file, it has some representation internally that we're not going to dive into, but an artist is going to control basically creating the geometry for a model. And Bevy is going to allow you to load that geometry into the game world so that it can be rendered. So how do we actually load the model? Bevy provides an asset server to load assets, including 3D models. For 3D models, Bevy has built-in support for the GLTF file format, which is a versatile and widely used format. Although it's not the de facto standard for other game engines like Unity, it's quickly growing in popularity. In this example, we can see how to load a model from a GLTF file. Note that you'll often see instead of GLTF, GLB. That's just the binary version of the same format. Asset server.load is basically tell the asset server to start loading this asset. It returns a handle to the asset, which is just a reference to that asset. If you have multiple handles, you can think of them as just pointing to the same thing. You can clone an asset handle to get another reference. Handles are reference counted. If you have no handles to an asset, it should be cleaned up by the game engine for you. That way you don't have to manage the ownership of the asset. Bevy abstracts that away for you. Note in the load function argument, when we specify the path to our model, we should include hashtag scene0 when loading a GLTF file format. This is because GLTF files find multiple scenes. So when we just want to load a single model that only has one scene, we still have to say scene0. Once your 3D model is loaded, you can go ahead and spawn it into the world with the scene bundle. The scene bundle allows you to take the GLTF file format and convert that to an entity hierarchy. An entity hierarchy represents all the aspects of your 3D model. So what does this look like? The scene hierarchy shows the ECS world how to represent the file that you loaded. Each of these entities in that hierarchy are going to have a transform. Each of them is going to have a mesh, a material, and potentially other components like animations. The mesh is a critical piece that holds the vertex and index data for rendering the model. We're not going to jump into how that works. Instead, we're just going to say geometry. And know that the artist creates most of this unless you're doing things like procedural generation and building your own meshes. For us though, all we know is there's a spaceship. The game engine can know about that geometry to apply things like lighting and shading. We're going to have a material, which is also defined in the asset file, that will specify based on the geometry how the light should interact with the geometry. So for example, we could use a material to say that this should be a more metallic object, or this object should reflect more light. But mostly the artist usually defines that, and then the game engine uses that properties to render the 3D object. We're finally here. We're going to do some hands-on examples. If the concepts didn't make sense to you and you just listen to them, watch this code example and then go back and listen to the explanation. It might tie everything together for you. All right, let's walk through the code example. First, we're going to update our existing components to be more in line with what we learned in this episode. In the last episode, we were just focused on the core ECS architecture. In this episode, we're going to start out by updating our spaceship to use Bevy's built-in transform component and update our velocity component to store a vec3. After updating from position to Bevy's built-in transform component, Bevy will know how to render our spaceship to the screen. We're making the components 3D capable and leveraging Bevy's built-in types instead of redefining our own version of them. Now, we're going to fix the code after making these changes. We need to update anywhere we use position to use transform. We can query the built-in transform component just like any other component. We're also going to add to our commands.spawn object a spatial bundle. This will give us the default values for a spatial entity at origin location 000 with no rotation and scale 111. If we run our code now, everything should compile and it will print out the transforms. Finally, let's update our comments and variable names to be in line with the new use of the built-in transform component. Next, let's take a quick look at the built-in bundles. I highly recommend that you read through Bevy's types using jump to definition in your code editor. They are mostly very well documented. The type documentation for Bevy structs and enums are usually very comprehensive and gives a lot of information on how you can work with that type. We can see that for the spatial bundle, spatial information is defined like visibility, computed transform, and global transform. We can also see the transform component here that we learned about in this video. Next up, we're going to define some plugins in order to better organize our code. To start, we're just bringing the spawn spaceship function into our new spaceship plugin, instead of just directly adding that system to main RS to the app. We're going to remove the add systems call in main and replace it with add plugin. This plugin isn't very useful right now because we're only defining one single function related to spaceships. Still, I recommend that you separate your code early so that as your code scales, you have it organized from the very start. This allows you to easily enable or disable parts of your code without affecting the rest of your code base. Now, we just need to add the plugin to our app in main, and we should be good to go. Let's do the same thing for update position and print position. For update position, we'll create a movement plugin, and for print position, we'll create a debug plugin. Right now, these will just both have one system, but as our app scales, we will add more things to our movement plugin and our debug plugin. Since all of our plugins are in main now, this file is getting cluttered. Let's split everything up and put each plugin in a separate file. This is a very useful pattern for any small to medium scale application in Bevy. It's something that I still heavily utilize in my game project with over 15,000 lines of code. Then, in your main file, you can just import the plugins and add them to the app, just like we did before. Just make sure to make your plugins public so you can import them in the other file. We also want to move all the systems associated with our plugins to their own files. When defining systems in a plugin, I like to keep them private, unless you are planning on importing them in another file, which is not usually the case for systems unless you are ordering them across plugins, which is something I would discourage. You can add systems directly in the build method of your plugin. Keeping the systems private encapsulates those systems and ensures that no other plugins import those systems and use that game logic. That way, each file has a clear responsibility for what it's handling. Before we can get everything to compile again, we need to import the Bevy prelude for all of our files, since we are implementing the plugin trait and referencing things like entities and transforms. Finally, since we define velocity in our movement file, we need to import that into our Spaceship file. Next, let's clean up our Spaceship file. We're going to add some constants for starting translation and starting velocity. We're going to use vec3 values here. We're also going to make a bundle for our Spaceship. Let's define its velocity and start pulling in a model so that we can see it rendered to the screen. This is very exciting because our game is very close to becoming 3D. In the Spaceship function, let's replace the spatial bundle with the scene bundle. This is the most common way to spawn a 3D model. Note that we haven't downloaded the asset yet, but don't worry, we'll get to that very soon. Our Spaceship has a starting velocity and a model, which is a scene bundle. We will use transform from translation, which is a helper method on transform that allows you to create a transform with default scale and rotation and a specific translation. Then we'll replace our old spawn spaceship function with a new one that loads a spaceship using the scene 0 from that GLTF file. In this case, we're using GLB since it's in the binary format. I've downloaded the asset file and put them in the asset directory. Note, a critical mistake is made here that the asset file has been placed under the source directory. Instead, you need the asset directory to be at the root level. If we were to run the code right now, there would be a warning in the console saying that the file could not be found. However, the code would still run, you just wouldn't be able to see any model. Next up, to render the 3D model, we need to define a camera. Let's go through our workflow again. This is going to be very similar to all the other plugins, and it's a pattern that you'll get familiar with over time. We're going to create a camera file, pull in the Bevy prelude, define a const for the camera distance, define a camera plugin struct, defining the build method. The build method is going to add a single system on startup called spawn camera. Spawn camera is going to take commands as an argument and spawn a 3D camera bundle. The bundle's transform is going to be built with transform from X, Y, Z. By specifying the transform, we can create a top-down perspective such that we can see the top of our spaceship as it navigates through space. Finally, we need to add the camera plugin to our app. If we run the game now, everything is going to be very dark. and the background will be black. Let's make our world brighter by adding 2 built-in resources to our app. First, let's add clear color and set the RGB value to be dark purple. Then, we're going to add an ambient light that's going to take the default color, white. We can add another color if we want a tint here, but we're just trying to make things brighter. By default, the game engine assumes that there is no light. Thus, the models will also look very dark when we spawn them initially. For the model to look normal, or similar to the models shown in asset previews online, you need to add a light source. If you run the game, you will notice that the spaceship may not appear on the screen, or only appear for a fraction of a second. This is because the spaceship is moving very fast, and it quickly goes outside of the camera's view. Remember that we defined our velocity as being 1 unit in the z direction, and our update position system runs that once every single frame. This means that it's moving 60 units per second, assuming the game is running at 60 FPS. Thus, since the camera is only 80 meters above the spaceship is going to go off the screen in under 1 second. It's also important to note that in most 3D games, the standard size for 1 unit is 1 meter. It's important to stick to this standard since other third-party plugins, such as a physics plugin, may use that assumption for computations. Even though we can simply adjust the speed to be slower, for example moving to 0.01 units, we also have another issue. The speed is not stable. Let's say your computer is overloaded and your game begins to run slower. This is going to correspond to a drop in FPS because your computer does not have enough resources to run all the computations required to render a single frame fast enough. If we used our existing movement logic, that means that the player would move slower or cover less distance per second. To make our speed constant, we need to pull in Bevy's built-in time resource. Time will tell you the delta time of a frame. That is the duration since the last update. You can use that delta time to move or change something based on how long it took to render that frame. This way, even if your FPS drops, you're still going to be moving at the same speed. This is very important because you want your game to be the same regardless of your computer's performance. In other words, you don't want the spaceship to zoom at faster speeds if the player's computer is fast. Once we've pulled in that time resource, simply multiply the velocity by time.delta seconds to update the transform. Assuming that everything is running at a constant 60 frames per second, the value will be approximately 1/60. Thus, this should also adjust our speed and make it so that we can see the spaceship on the screen for much longer. Note, the translation is a vec3. We can simply add the velocity, which we've also defined as a vec3, to that translation. Bevy's built-in vec types have a lot of nice functions like dot product, cross products, etc. This is another reason to use vectors instead of defining a custom component with X, Y, and Z fields. Let's go ahead and fix our earlier mistake by moving the asset directory to the root of the project. Now, the spaceship model should be loaded correctly. And that's it. Our spaceship is now moving at a snail's pace across the screen. In the future, we're going to continue expanding this example by adding user input such that we can control the spaceship. We're also going to add ability to spawn and despawn asteroids. We're going to work on basic collision detection, and we're also going to continue to dive in to the core pieces of Bevy ECS. We're going to cover things like run conditions, system ordering, and events. If any of that sounds interesting to you, I hope you'll stay tuned. I want to thank you all again for watching. As I mentioned in the first episode, this is my first time making a YouTube series, and any feedback at all is appreciated. And with that said, I'll catch you all in the next episode.